All right. Thanks everyone who's joining. Welcome to the F word. So I started last year just doing a couple live streams, just showing you what I've got going on in a coding project I'm working on. I figured, this year I want to try something a little different and give you some context for what's happening. So what I'm primarily working on is a piece of software called the Spectral Element Library in Fortran. And the whole point of this library is to provide some tools that can be used to solve conservation laws. So if you're in the sciences, you know what this kind of looks like. Generally, what we're trying to do is to solve a partial differential equation for a set of what we call prognostic variables. What that looks like, we have a time derivative of some variables, and if you're thinking like fluids, this can be things like density, momentum, pressure, energy, things like that. That variable changes with time due to the divergence of a conservative flux, which is a vector, and that's going to be balanced by some internal source terms. So like I said, we could be doing this with Euler's equation. This is primarily where I'm heading with all this stuff. So right now we're just working on a simple advection solver. But like for Euler's equation, what you might see for those prognostic variables, for the S guys there, you might have a density, 3 variables for momentum, so rho u, rho v, rho w. You could have total energy, right? And in some cases, like if you're doing ocean modeling, you might have other things like salinity thrown inside of there. Your fluxes, you'll have the typical advective fluxes that might be inside of that as well. So for your density, you'll have just really the mass flux, so rho times the velocity vector. For the momentum terms, you'll have the advection of momentum and then a pressure gradient. So you have rho uu, rho uv, rho vu plus p in the y-hat direction, etc. Right, and of course, you could also have other source terms in there. So if you have like viscous fluxes or other, chemistry types of things going on, other physics, you could represent those in Q. Of course, you could also do simple things like what we're working on now is the advection equation, where S might just be the concentration of a scale of a bit of tracer that's moving around in a fluid. So we can call that C, for example. And the flux that you end up having for something like that would be a velocity field times that concentration. If you're also doing diffusion in there, you might also add in a diffusivity coefficient multiplied by a gradient in that vector as well. And then your sources could be any type of source that gives you an introduction of that tracer into your system. So this is kind of the gist of what we're getting at, is how do we solve numerically this general conservation law, provide a set of tools to essentially allow us to compute divergences. And in some cases, when you have source terms, there could be other things you need to calculate, like gradients, curl operations, things like that. So we basically want to be able to do calculus operations in 1, 2, or 3 dimensions on various grids. And where we ended up at the end of last year was a bit of code that allows us to solve advection-diffusion. And qualitatively, things were actually starting to look all right. And where we're at right now is trying to verify spectral accuracy. So we're trying to make sure that what we actually coded up is indeed what we wanted to have. So there's a bit of theory behind how we do that. And I put out some links in the bottom of the YouTube video for a few different references. So there's 2 books. One is Implementing Spectral Methods for PDEs. And then there's a collaboratory notebook that's out there. Just if you go through that, you can hit request access to it, take a look through the notes that I've got there, as well as some interactive Python code to get you an idea of what to help you build a little bit more of an intuition for the stuff we'll be talking about today. And then what we'll do from there is kind of dive into the code and actually start implementing this stuff. So my hope is that like these whiteboarding, blackboarding sessions build a little context for what we'll be doing here in a minute. So the what we were trying to do in spectral element methods is to approximate functions ultimately with an interpolant, and then we calculate calculus operations by doing calculus on those interpolants, because we know formulas for those. and to understand where how this works and like ultimately what we're trying to get to today is verification of our methods. What we're going to show, I just want to kind of give you a brief sketch of what the error behavior is like, because essentially the methods that we're going to be putting in today are supposed to be trying to replicate some of this theory. So the basic idea is we try to approximate functions as the summation of essentially what we call modal coefficients, so we'll call these f hat, weighted by some basis functions. And the basis functions that I'm using in self are the Legendre polynomials. So we'll call these L sub k of x. We'll do a sum of k from 0. Now, there's a little bit of theory behind this. Essentially, as long as the function f here is what we call square integrable over a domain, so let's restrict x within -1 to 1. As long as it's square integrable, in other words, the integral of f over this domain is well defined, or its square is well defined, we can write this decomposition. In other words, we can express this function as a linear combination of Legendre polynomials. Now, of course, this infinite sum is impractical to do on a computer, so what we typically do is truncate. So you'll do a sum over it's basically a finite sum using those modal coefficients, right? And of course, whatever is left over is what is the error. So it basically, if I split that sum up to n, and then I have the remainder, is that sum from n plus 1 off to infinity, f hat k, lk of x. Okay, so this term here on the right-hand side is really the thing that I'm throwing away, so it's going to be the thing that houses all of the error that I'm going to incur based on doing this sort of finite truncation. So the notationally what we write this as, this is called the projection of f onto the polynomial space of degree n. So we're basically saying any function, we're going to approximate it by a polynomial of degree n, and then we're left over with this error. So this is called the projection error. Okay? And we can quantify the size of this error, right? If you were to basically move the projection of f over to the left-hand side of the equation here and take the norm of that, what we're left with, okay? So that's this guy here. The squared is the squared norm of the projection error. If we apply that operation on the right-hand side, and I'll kind of dive in here a little bit to define this operator here in a second, but essentially what we get to is a sum from n plus 1 to infinity of the absolute value squared of those modal coefficients, and then the magnitude of these Legendre polynomials. And just so I'm not spending so much time on theory during the live stream, the collaboratory notebook, if you were to go ahead and request access to that, that will have a lot of the details about that kind of fill in some of the gaps here. But essentially what we're getting at is that this error that we're trying to measure, it depends on the rate at which these coefficients decay. And this, so if you were to, if you want to know the error, we need to know those modal coefficients. Well, there was a lot of folks back before I started working on this, a long time before. There's theories that predict what the rate of those modal coefficients and how those decay as you increase n. And I show you just a couple plots here. I have two functions here on the left-hand side. So one is this orange function. This is like a Gaussian function. It's nice and smooth. Has real. It's what we call complete. And then we have this blue function here is like a hat function. And if you it's really the absolute value of x, of course shifted off to about a quarter. Now the idea here, what I want to illustrate for you, is that the smooth function essentially has modal coefficients that decay exponentially fast. Boy, we're getting spammed. Let me go ahead and kill those. So Right, the idea here is on those smooth functions, the modal coefficients decay exponentially with the polynomial degree. So as I add more Legendre polynomials in there to represent my function, the faster those modal, I guess the less it really modifies my approximation. So in the orange, what I'm showing there on the right-hand side are these Legendre coefficients for that Gaussian, and then in the blue are the Legendre coefficients for that Heaviside, sorry, not the Heaviside step function, but the absolute value. And the reason why the absolute value has a slower decay is because it has a discontinuity in its derivative, particularly right there at x is a quarter. There's a jump discontinuity in its derivative, and what we end up seeing for what turns out to be the case is that if you have a discontinuity in the kth derivative, you'll get n to the k convergence. In other words, it'll be polynomial convergence in the solution. If your function is what we call complete, it has infinitely many derivatives, and those derivatives are nice and smooth, you get this exponential convergence. Now this bottoming out here is actually coming from round-off error. We're doing double precision arithmetic here, and we're bottoming out at about 10 to the minus 15. So that's the only reason this curve actually slopes off. So if I were to go to quadruple precision, this curve would keep going down. Now, so this is the basic idea, all right? So I have a function. It could be a Gaussian. It could be anything out there, and I basically want, as long as it's square integrable inside of some domain, I can represent it as a linear combination of Legendre polynomials. There's other polynomials you can use. There's Chebyshev has been used traditionally as well. It's got some nice properties in how it relates to Fourier transforms. So they're very computationally efficient. Now, in the context of what I'm doing in self and everything there, we primarily use Legendre polynomials. So that's the basic idea. So that's the first error that we actually incur. So what we really do is in practice, if you think about this problem, right? If I represent a function, let's get the pen back here. If I represent a function by its projection, the degrees of freedom that I end up with are these modal coefficients, which is not super great to work with out of the bat, because typically when you're designing a numerical solver, what you want to have on the output is a function that depends on space. Now, certainly, if I store what these Legendre polynomials are, or I have a function that I can use to calculate them, and I store these modal coefficients, I can recover the solution on a grid. In other words, I can interpolate. I can get a function at some grid point x sub I by simply evaluating this decomposition at that particular point, right? And if I give it a grid, of course, I can recreate the solution on a grid. But rather than kind of breaking it down into a two-step process where I basically create I plug in this projection of the function into my PDE, and then I go through and I solve for the modal coefficients and then back out the solution on the grid, you can just use an interpolant directly. So an interpolant, instead of basically working with these f hat k's, what we really want to do is we want to approximate the solution with, and I'll call it I sub n of f. K is 0 to n. Okay, and we actually have a different kind of coefficient there, so I'll denote it with an f tilde. Okay, and it'll still have the Legendre polynomials in there, and the difference between f tilde and this f hat is in the way that we choose to determine what those values are. So the first one, the f hat k's, I should have mentioned this in the beginning. The Legendre polynomials are fairly nice because they satisfy a pretty cool property. It's called orthogonality, where if I have Legendre polynomial k, if I multiply it by Legendre polynomial j, and I integrate over that domain, I get the Dirac delta operator. In other words, actually, and it's also multiplied by the magnitude of LK squared. In other words, if I want to go through and calculate those f hat k up here, right? I can just multiply by Lj of x, integrate from -1 to 1, and then I get a system of equations that allows me to back out those f hat k. Now, the interpolant, the difference with the interpolant is that what we're going to do is, rather than determining these coefficients by a continuous integral, we actually determine them by discrete integration, which does incur what we call an aliasing error. And it's quite lengthy to go through and show you all those details, but essentially there's two bits of criteria that we ask for the interpolant to satisfy. So one, the interpolant of f at xi is got to be equal to the function at those points. So you give me a grid of points, I tell you the function values there, and I make sure the interpolant matches the function through those points. And of course, like I said before, we can recreate this provided we have modal coefficients. And if the modal coefficients are computed exactly using exact integration, that's great. The problem is, on a computer, we don't normally do exact integration. We use what's called discrete quadrature. So that formula I wrote down before, remember I had this LK, LJ integrated from -1 to 1 dx. Clean that up a little bit. This is called an inner product, and so you'll probably see me use this notation. We'll have a left caret, LK, LJ. All right, so if I write it this way, it means we're doing it continuously. What we're going to do is approximate this with an inner product that uses discrete points. And what that inner product with discrete points really is we're doing a sum, I equals 0 to n, LK xi, LJ, LJ xi, and we multiply by some weights. So what we're essentially doing is replacing a continuous integral by a weighted sum of the integrand. And the hitch here is, what we want to do with this discrete quadrature is to determine the xi, so where we evaluate those Legendre polynomials, and what weights we apply so that orthogonality is preserved, right? And we want to preserve orthogonality, hopefully, for at least polynomials of degree 2n, because if I look at this is a polynomial of degree n, here's another one, so the polynomial degree of the integrand is 2 times n. And again, if you check out that collaboratory that I've linked to in the description, there's a bit more of a derivation that shows where it comes from, of course, with links out to that book I mentioned, Implementing Spectral Methods for PDEs, where you'll get enough information to kind of get you familiar with where that comes from. Now, the short end of the story is that we can choose those x, I, and those weights, those omega i's. It's called Gauss quadrature. So the points we end up choosing end up being the xi are the roots of the n+1 Legendre polynomial, and the weights are calculated based off of integrals of the nth Legendre polynomial's derivative. It's kind of bizarre, but that's how it ends up working out. And to give you an idea of kind of what those look like, if I'm looking at a line segment from -1 to 1, the Legendre Gauss points don't actually lie on the endpoints. They're very tightly bounded in towards the end. You'll have one at the center, and they're unevenly spaced within this particular domain. So that's basically the gist here. So once we go from so the approximation we're doing, right, is we're replacing the function with an interpolant. The interpolant incurs, one, a projection error because we're projecting the function onto the space of polynomials, and then because now we're using discrete quadrature, you get what's also called an aliasing error. So at the end of the day, what we're doing, f of x is going to be approximated by the interpolant of f, right, which is, we're going to write it actually in a different form than what I have above. We can write it in terms of its nodal values, so fk, so these are the function values at specific points in space, and the polynomials that we replace them with, I put lowercase l here. These are called the Lagrange interpolating polynomials, and Lagrange interpolating polynomials particularly satisfy that criteria there. Now, the cool thing with spectral element methods is the points where we fix, basically that we interpolate through, the knots of the interpolation are the Legendre-Gauss points. So that's the gist of it. So now that we have a way to approximate a function, and we know that the error is the sum of a projection error and an aliasing error, both of which are spectrally accurate. And what that means is the error depends on the rate of decay of the modal coefficients. There's a lot of work out there that shows smooth functions enjoy exponential decay in the error as you increase n, which is really nice. Or if you have some discontinuities in the solution, the error depends on which derivative is discontinuous. And that's what we really mean by spectral accuracy is the error decay rate does not depend on the method you're using. It really depends on the function you're approximating. So let's look again, I want to give you a feel for what's been implemented in Self. The easiest way to do this is to look at a 1D problem and then kind of hands wave my way through what we would do in higher dimensions. So if you think about 1D advection, you have, let's say, a function that depends on time. We'll have, in this case, we're just going to do something that advects to the right at speed 1 is equal to 0. We have the initial condition. Sorry, let's just do the boundary condition. And I need to put that at -1. I'll call that g of t. And then the initial condition, so u at x, t is 0, is u naught of x. So this is our initial boundary value problem that we want to solve. Now, in practice, what we often do is if the domain, so here I'm trying to keep it easy so I'm not introducing too much complexity. I'm going to keep the domain at -1 to 1, particularly because this is a typical reference domain that we work with. Now, in practice, if this were from A to B, for example, what we would do is introduce a coordinate transformation to map from the line segment A to B down to -1 to 1. Okay, and then we would then replace the derivatives with basically by doing chain rule to get out derivatives in the computational or that reference domain. But again, just to keep things easy for today, because that stuff I will be covering later on this year. We'll be looking at coordinate transformations, things like that. The simple thing is we're going to start there. And what we work with primarily are what are called Galerkin methods. And so, and specifically for these hyperbolic problems, we use what's called discontinuous Galerkin. So what that means is, in general, what I'll do if I am on A to B is I'll divide that line segment up into multiple elements. And inside each element, I'm going to solve that boundary value problem. And over here on the complete left side is where I'll enforce that boundary condition. And remember, since things in one-way advection go one way, I only need that boundary condition here on the left side. So the idea is we'll divide that domain into multiple elements. Each elements get mapped to this reference domain on -1 to 1. And then at the interface between each element, we compute a flux between them to couple everything together. That's the big picture. To get to the weak form that we're looking for the DG methods, what we're going to do is, one, we're going to approximate u by a polynomial, so particularly by its interpolant. So we have u is approximated by interpolant of u, so it's sum k equals 0 to n, uk, lk of x. And again, these are the Lagrange interpolating polynomials. That these uk depend on time. And then two, what we're going to do is we're going to multiply the PDE by each of the Lagrange interpolating polynomials and integrate over the domain and then perform integration by parts once on this term. So instead of writing all that out, I'll show you what that looks like. So we do du dt times Lj of x dx. We integrate from -1 to 1. Okay. and we're going to add to it minus 1 to 1 du dx, okay, Lj of x dx. Okay, so if I were to plug in for u the this guy right here, the interpolant, let's look at the first term. So what I get is the integral minus 1 to 1 sum over k equals 0 to n u. I'm going to use an over dot for that time derivative, k lk of x lj of x dx. Okay, so that's the first two approximations. The next one, like I said before, instead of doing continuous integrals, we're going to do discrete integrals. So this becomes another, oops, that is not the sigma notation. There we go. We're going to do another sum here. So we'll do a sum over I, 0 to n. So remember, the reason why this sum is over n is because we're using those Legendre-Gauss points of degree n, which is kind of nice. So we get a double sum. And things are actually going to drop out pretty nicely here in just a second. So you have u hat k, lk xj. Sorry, that's I. We're evaluating at the xi points. Lj xi. And now we have omega I. Now remember before, those Lagrange interpolating polynomials satisfy this criteria. In other words, the interpolant matches the function at the interpolation knots, and what that allows us to do, this guy right here becomes the Kronecker delta delta ki. So only k equals I survives this summation, and this one also becomes Lj I. So j equals k equals I only survives. So this all reduces down to u dot j omega j. And if you've done finite elements analysis before, you know this matrix that ends up on the front when you do this integration with a different bases, that mass matrix, it can in some cases be full. It's not sparse. In spectral element methods, in particular these nodal spectral element methods, it's a diagonal matrix whose entries on that diagonal are the Legendre-Gauss quadrature weights. Now you'll probably see other people who do Legendre-Gauss-Lobato or Chebyshev-Gauss or Chebyshev-Gauss-Lobato. The idea still holds. We still do this, but now everything is dictated by, again, where you place those quadrature points and the values that you use for those quadrature weights. Okay, so that's the mass matrix. I'm going to go ahead and remove this line up here, and we're going to do, we need to do an integration by parts. So if I do integration by parts, if you remember those rules, so go back to Calc 2. All right, so we have uxlj dx. So that's going to give me u times L at the boundaries of the domain, so minus 1 to 1. I'm going to take the difference of that function at the boundaries. Then I'm going to subtract the integral minus 1 to 1 u, and now we move the derivative over to the Lagrange interpolating polynomial. Now remember the weak form, the nice thing about the weak form is this is very subtle. Because we did integration by parts, the weak form doesn't require that I actually evaluate a derivative of u. It requires that I evaluate derivatives of the Lagrange polynomials. And so this is where the whole discontinuous idea comes from, is that we restrict some smoothness, or we remove some smoothness constraints from u and put it onto the polynomials. And then, of course, the way we end up handling this over here between elements, it changes things around quite a bit. And so what we typically do, so in this case, u is our flux vector. The other part here is we replace the flux at the boundaries with what we call a Riemann flux. So I'm just going to write that as f star minus 1 to 1 integral u L prime j dx. Okay, and if you'll forgive me, I'm going to go ahead and remove this line here, and then once we're done, we'll kind of write everything down in the discrete form, and then we'll kind of go over what happens in multiple dimensions. Okay, so we're going to do the same thing we did before for the moment. I'm going to leave this, this boundary term alone. Let's focus on how to write this term. So let's go ahead and get rid of this up here so we have some space. And let's start with that integral. So again, we're going to go ahead and substitute in the interpolant representation for u. So again, that's the sum. What was I doing before? It was k equals 0 to n. uk, we have lk of x, and then I have L prime of j of x dx. And let's go ahead and now we're going to go from continuous integration to discrete integration. So we get another sum. We get I equals 0 to n. We have a sum k equals 0 to n. uk, lk, xi, L prime j xi, and then we have those quadrature weights, those omega i's. Okay, so from here, what we do, right, is this term, we have Kronecker delta ki, but now on this other term here, we actually have a derivative of the Lagrange interpolating polynomial, so that doesn't actually go away. So we still have one summation left. We are able to get rid of one of them, particularly the k equals I. Sum goes away. So what I'm just going to do is just leave this as sum I equals 0 to n. We get ui, because now remember k is I, L prime j xi omega I. Okay. Now if I were to write this in, basically what this ends up looking like is somewhat of a matrix vector product. I have a vector of solution nodal points here. And then I have, for each j, right, for each j, I have a series of entries that I need to multiply by in order to calculate this derivative. So if I were to piece this all together, so far what we have in the discrete form, so the discrete representation of our PDE is, if you're familiar with doing numerical PDEs, this is what we're calling a method of lines. So we've discretized in space but haven't done so in time yet. What I have is u dot j omega j for that time derivative term. I've got my boundary terms. So my f star, my Riemann flux, Lj, evaluated at the endpoints, minus, then I got that sum I equals 0 to n. ui L prime j xi omega I, and this, omega I, and this is for j equals 0, 1, so on out to n. So what's cool here is we now have a discrete ODE system. So we went from a partial differential equation to a system of ODEs where the degrees of freedom in that ODE are the nodal points of the solution. So unlike finite element methods or even modal spectral element methods, we're not having to work with those modal coefficients and then reinterpolating, to get the solution on a grid. This is essentially what we do. This is, of course, very simple in 1D, but you can apply the same idea in 2D. And the gist of how that works is, so remember in 1D what we did was f was approximated by the interpolant of f, which was just a sum I equals 0 to n. We have nodal points Li of x. Now in 2D, you just do a tensor product of the 1D, right? So if I were in 2D, so this is 1D. In 2D, what we do is we have a sum over j, sum over I. I'm not going to put in all that stuff there, but we know there's a going up to n. And now we have Fij, Li, x, Ljx. And you could basically repeat this process, go through the conservation law you're trying to solve, do an integration by parts once on the conservative flux term, substitute this in for your solution, for your fluxes, for your source terms, and kind of work yourself out through to the end there. So again, I'm working on a set of notes that really provides a lot of the details on the 2D and 3D derivation, and I'll be getting those posted on our Open Collective page as soon as we're done. Getting those ready. The collab notes, again, should walk you through a good deal of what we did up to this point in 1D. Now, the point to me showing you this is that in the process of doing this, the only errors I've incurred are the truncation errors and the aliasing errors, which are supposed to be spectrally accurate. And in other words, if I know the solution to an advection problem, for example, if I started with a Gaussian centered at 0 and I advect it to the right at speed 1, you know, a few time steps later, I should be able to calculate what the exact solution is, and then repeat this process over and over, increasing n. And as I increase n, if the solution is expected to be a Gaussian, I should see an exponential decay in the error curve. And that's essentially what we're trying to do today for the 2D and 3D advection problems. If you do have any questions on any of this stuff, feel free to post your questions in the chat. I'm going to go ahead and get everything transitioned over so we can start coding up some of the bits that we need to do verification of spectral accuracy.
to break that subroutine up at some point. That thing is massive. we go. Great. That didn't work. Oh, it's an old file. Gonna run and get some water. Right, I should probably put a print statement in there. likely need to drop the time step as well. Looks like we bottomed out there, but yeah, outside of that last one, we're getting spectral convergence. So now I just got to code up basically in the model a loop that goes over the polynomial degrees and also reduces the time step at the same time to keep the same CFL number. But that's about it for today. I think I've gotten what I wanted to, and we're looking like we're on the right track. So between now and next live stream, yeah, I'll be getting the loop in there to automate basically sweeping through polynomial degrees to create a chart to look at the spectral convergence. Anyways, thanks for tuning in. We'll be back in 2 weeks. You can check out the Open Collective site that's linked in the description below for more information on upcoming events, and also you can get a hold of those references I mentioned at the beginning of this live stream, including the Google Colab notebook and a handful of papers and books that were used to inform all those notes. All right, guys, thanks for joining. I'll catch you next time.